Hello, good afternoon. We are from the Colorado School of Mines, and we had the Crystal Parks District. Sorry, technical difficulties. Why is this not changing? Okay, Colorado School of Mines is dedicated to implementing ideas to improve Earth, energy, and the environment. I am Cami Devoto Noonan. I'm a senior studying engineering physics, and I was in charge of the conceptual system design using SAM and PV watts.
My name is Nathan Collins. I'm a senior studying electrical engineering, and I was responsible for the distribution system impact analysis and OpenDSS.
I'm Cara Fragamini. I'm also a senior, and I'm studying civil engineering, and I was in charge of the construction and development plan.
Hi, I'm Luke Crow. I'm a senior studying civil engineering, and I focused on the financial modeling for the project.
Hi, I'm Paul Slade. I'm a senior studying mechanical engineering, and my primary focus was optimizing the battery dispatch strategy.
So a brief summary of our conceptual system design. We decided on 2 locations, the on-site location being all 5 Crystal Parks buildings owned by JBG Smith, and the second being an off-site decommissioned landfill located in West Fairfax County. A few important details about our systems design. Our team decided on a lower tilt angle for the rooftops to save space while not sacrificing too much energy output, so we'll use a 10-degree tilt. From the advice of an industry expert from McKinstry, we decided to use solar panels manufactured by Canadian Solar, which is a Tier 1 company. We will use bifacial panels at the landfill site to increase efficiency by about 20 to 30%. And as you can see, we will not include a battery system, which will be explained later in the presentation. Our team used Aurora Solar to build these models. Our biggest goal for the rooftops was to use as much space as possible without interference of shading. The rooftops will encompass approximately 5% of the electric load for our district. And located approximately 23 miles west will be our landfill system. For our landfill system, with the addition of the rooftop systems, we will be able to offset approximately 100% of the electric load for our district. We will use multiple arrays with one central inverter to accomplish this. Lastly, here's a plot of our expected operation using several different softwares. As you can see, SAM has a much higher output because we were able to model the bifacial panels in SAM. And again, just to hit this point home, the sum of our system will be able to approximately offset 100% of the electric load given to us.
All right, now I'm going to talk about the distribution system impact analysis. So basically, we took the OpenDSS model and added in a PV system with data from SAM and Aurora Solar. Then we duplicated that script and added in a 300 kilowatt hour, 100 kilowatt battery defined as a negative load. As you can see, the results yielded a minimal increase in voltage over distance. The PV system under maximum irradiance with and without the battery both only show a slight increase in voltage and shouldn't require any special control to install. Just to hammer this point home, this slide shows the yearly voltage profile for the 2011 building. The other 4 buildings yielded similar results. There are only a few spikes in voltage that may exceed 2,520 volts or the upper limit on voltage, but we believe these are due to outages and don't pose any serious issues.
Sometimes simplifying a design will actually make it better, and this was a tough decision we learned. We're not going to be building a battery, but we still decided to optimize the dispatch and distribution of a battery for JBG Smith because battery prices will drop in the future, and it's possible that they will want to build one in the future. The battery we optimized was a 300 kilowatt hour battery per building with 100 kilowatts of output. We optimized using financial savings in ReOptLite. Primarily, those financial savings are coming from load shifting. We have an extremely high on-peak rate and an extremely low off-peak rate, and so we decided to try and save JBG Smith some money by transitioning the energy consumption from the on-peak period to the off-peak period. Now, this utility rate is important to understand to explain why a battery is just not going to be economically viable. The first number I want to bring your attention to is in the bottom left corner, this blended cost of electricity. This is essentially a weighted average of all of these different rates. The second number I want to draw your attention to is the 24 cents on peak period for Class A days. So we have a large difference there between the average price and the on-peak rate. Now, one thing to mention is the average price, this blended cost of electricity of 3.4 cents, is already significantly lower than the average industrial and commercial use energy rate experienced in this area, which is around closer to 8 cents. And so that was our first hint that a battery would not be financially viable. The second hint that a battery would not be financially viable is because there are only 28 Class A days per year. And as I mentioned, those Class A days have the greatest opportunity for financial savings using load shifting. On Class B and Class C days, the difference between the on-peak rate and off-peak rate is just too small for JBG Smith to have significant savings. With a battery only providing value to JBG Smith for 1 month out of the year, we just could not justify the significant capital costs. Those capital costs are dropping, however. NREL predicts that the prices of energy storage will drop significantly in the next 5 to 10 years. And so for our simulated battery size, the net present value today would be $83,000 lost for JBG Smith. However, if they wait about 10 years, it's only $9,000. Since we had to look for other opportunities to provide JBG Smith value in this battery, we looked for resiliency. However, we cannot know exactly how highly JBG Smith values resiliency. And so we're going to leave that option to them. This net present value is essentially an estimate of the price they would have to be willing to pay to have a resilient power system that is able and capable of withstanding power outages. If they're willing to wait, which we recommend, then they will have a much more financially sustainable battery system.
Okay, so I'm going to go over some of the financial modeling we did for our designs. One of the biggest challenges we faced in our financial models was the district's low cost of electricity that Paul kind of mentioned. And we split our models into 2 separate models. One to look at the on-site rooftop models, and those we kind of used the 2011 building as a example case, and we modeled them as ownership models. And you could see that this system has a fairly long payback period of 22 years, and this is primarily due to that really low cost of electricity in the district. We modeled a range of cost estimates out into the future, and we estimate that it will be at least 10 years until system paybacks are approaching the 7 years that JBG Smith asked about in the district profile. That being said, this system has a 2.76% return over its 30-year lifespan, so it's not great. It's close to break even, but the system will be able to offset 5% of the building's annual electricity usage. And then looking at the offsite landfill, we modeled that as a virtual power purchase structure. So in this model, a developer would actually build the project, and then the district would contract to purchase power from the project. And we tried to model, or we tried to balance in our models the developer's return on the project with the value that the district would get from purchasing the power. So we said that if the developer offered a 6.3 cent per kilowatt hour price to the district, that they would be able to generate a 4.75% return on the project. And we think this is a low return. Typically, we think a project like this would generate a market return of 7 to 9%. And the reason it's low is because we had to balance the district side of this. So on the customer side, you can see that the price offered to the district is a flat price, and the utility price is escalating over time. So initially, the district would actually pay more for their power, and towards the end of the agreement, they would be paying less. Over the 20-year term of the agreement, it would cost the district about $4.6 million above what they would pay just by purchasing electricity from Dominion. However, in exchange for this, they will be able to offset 100% of their usage and meet some of their other sustainability goals.
Okay, so moving on to the development and construction plan, we are going to start with the rooftops. This area, Arlington, is super close to DC, and so the development market is very saturated. This is a rendering of Amazon's HQ2, which is planned to be built in the next 2 years. And from my lovely annotations, you can see the Crystal Parks district is just adjacent to this. So there's lots of new buildings going up, a lot of exciting new projects. And so the development environment is very rich in this area. Moving on to the landfill installation, as Cami said, we're going to use a capped landfill in West Fairfax County, which is 23 miles away. The landfill cap is composed of a clay layer and then an impermeable membrane interspersed with gas vents to let the methane out at periodic intervals. This means that our mounting system can't puncture the ground at all. So helical piles or any other type of foundation system is not allowed at the landfill because the impermeable membrane has to stay intact. To overcome this, we decided to use a geoballasted system, which will be shown later. And this also helps reduce the installation costs as well as reducing the labor. We also developed a risk mitigation plan to reduce the project's impact on the surrounding citizens. The first tenet of this plan is mutual benefit. So since we're so close to DC, there's tons of universities and colleges within 10 minutes of the Crystal Parks district. And we think this would be a great opportunity for JBG Smith to show how engaged they are with the community by inviting engineering students or other groups from the university to come visit their project, see what a construction site is really like, and get some real world experience, kind of like the Solar District Cup is doing for us. The second part of this plan is minimal disturbance, which the surrounding businesses for the landfill are shown in this photo. As you can see, most of them are already heavy uses. There's the Department of Public Works, there's a bus lot, and a recycling and disposal center. So since the landfill was already used for heavy construction traffic and they had trucks driving in and out and noise all the time, we don't anticipate that construction will really impact the surrounding businesses too much because they were already used to it. The final prong of the risk mitigation plan is ascending arbitration. This basically means that JBG Smith should start with the least invasive type of mitigation that they can. So if a community member has concerns, don't start with a lawyer, start with community meetings or a dedicated liaison. Only after these solutions have failed should they move to legal action, arbitration, and mitigation. So because the development market in DC is so active, we've proposed innovative construction methods to help reduce cost. On the left, you can see our geoballast system, which is basically a wire cage filled with 3.5-inch quarry rock. To further reduce the cost, we propose to use recycled concrete from the disposal center next door as the ballast instead of nice quarry rock that was just excavated. In addition, we are going to use the Ready Rack system by APA Solar, which puts the panels all together and then puts them on the rack rather than putting them on the rack individually. From this GIF, you can see that this 3-man team with a backhoe and a skid steer is able to install the panels with no trouble. Traditional installation methods would take much longer and require expensive, heavy equipment like a front-end loader and a bulldozer. For the optimization strategy, we focused on reducing labor costs because it's so expensive in this area and improving efficiency. For the on-site installation, this is encompassed by the low tilt angle to minimize the panel spacing so that we can fit the most panels on the roof as possible, and aligning the construction timeline with new development, potentially Amazon's HQ2 or another building that is going up in that area to minimize the construction impact on the surrounding areas. For the off-site installation, the location is very innovative because no one really wants to rent a capped landfill. You really can't use it for anything because you can't drill into the ground. One of the things you can use it for is for a ballasted PV system, which is perfect for us. The recycled concrete used as a ballast reduces the material costs, and the bifacial panels that we've chosen will be more efficient because they can capture more solar energy per panel.
Okay, so how will our designs meet the district goals? If fully implemented, our designs will allow the district to offset 100% of their annual electricity usage with clean, renewable solar energy. The rooftop systems will immediately reduce utility bills. Our designs will help the district reduce their carbon footprint and address climate change. They will also be in compliance with the DC Clean Energy Omnibus Bill, which requires that all businesses be 100% renewable by 2032. And they will further meet some of their other sustainability and efficiency goals. We also think they have an opportunity once they implement our designs to be recertified from LEED Silver, and we think they can achieve LEED Platinum. So thank you for your attention, and that concludes our presentation. We'd like to open it up for questions.